This is Group 6 DTP video presentation, and our problem statement is how might we accurately predict the carbon footprint of food production across different types of crops and livestock based on production volumes. These are the details of our model. The dependent variable is the carbon emissions, and the independent variable is the volume of food produced. We use mean squared error to minimize error and aim to predict the emissions of various crops and livestock. Thus, we aim to encourage the production of food with lower emissions and reduce the production of high emission food, guided by insights from our model. So here's the line of code. After importing the data from the relevant sources, we first clean the data, and then we reshape the data according to year and area, after which we rename the columns, and then we sort by year and area. Last but not least, we merge the data sets on common columns. Next, we drop the specified columns and rows based on the findings from the MU side, and we excluded data from 2022 because the year is missing data. Afterwards, we changed the unit from tons to megatons. We add a new column for B to the power 2. We move the B to the power 2 column next to the beef column. Get the list of columns, find the position of the beef column, and then remove beef to the power 2 from the list and insert it after beef. Lastly, we will reorder the data frame. As we do a scatter plot for the data, we realize that emissions will increase with the food production at a decreasing rate, as seen in all the graphs here. As seen from the graphs, vegetables were selected due to their widespread production and consumption, while beef was chosen because it has the highest global carbon emissions and significant global consumption among meat. So here's our analysis of why emissions might increase at a decreasing rate, using beef as an example. So firstly, efficiency gains with scale. Larger scale beef production systems tend to optimize resources, reducing emissions per unit of production. For example, improved feed efficiency or digestion management reduces methane emissions. Secondly, shift in production practices. High production regions or producers may have already adopted lower emission technologies, meaning each additional unit of beef contributes less incremental carbon compared to earlier levels of production. Thirdly, diminishing marginal emissions. As production increases, some fixed emissions, example infrastructure energy use, may be spread out over a larger output, reducing the per unit contribution to total emissions. Last but not least, different regional contributions. If regions with low emissions per unit of beef dominate high production levels, the total emissions increase might still reflect their inefficiencies, leading to a decreasing trend in the rate of increase. Now going back to the code, we prepare our features and targets to create a linear regression model, and the code is used from the cohort solutions. Now we can build the model by calling all the functions above. So first we extract features and target, split the data with random state equals 130% test size, normalize the features, change the feature columns to numpy array and append the column list, change the target column to numpy array, and then you can call the gradient descent function and call the predict method. So we will be mainly using mean square error as a method to evaluate the model, and over here you can see this is the current value, and this is the results of our prediction, yellow being the prediction and blue being the actual results. For improving our model, we use hyperparameter training, so using different values for the random state and test size, and then find out which are the best two values to get the lowest mean square error. So basically, here's our code, and at the end we find that the mean state error has been decreased to 2.49. In conclusion, since our mean square error is 2.49, is a moderate value, and it means that the predicted values of the model are acceptably close to the actual data. And since our R squared value is 0.89, which is very close to 1, the model is a good fit to explain the relationship between the target and features. our model proves that the level of carbon emission is linearly related to the volume of food produced. So we have predicted the carbon emissions of farm products based on the production levels. And we come to realize that the production of beef should be reduced and the production of vegetables should be increased to minimize the carbon footprint of agriculture based on our model.
So now this is our vocarium for our web app. So to start our web app, you want to right click the project folder and open an integrated terminal. Oh, yeah, so as you can see, it's already open. So what I want to do is do Python app.py. Yeah, so this uses Flask to run, which is part of the requirement, which you will, see, it's using that. And now for this web app, what we want to do is the carbon emission analysis of crop and livestock. So what we want to do is to compare two different crops and compute their emission based on their production volume. So right now we have two different crops. So right now we can now compare the two of the same crops. That's just a little feature we added. Now if you want to compare beef and milk, here's our scatter plot with the actual value as well as the predicted value based on our code. And here's the scatter plot for milk, and then there's a little evaluation here that compares the two. So it uses the predicted value from our model, and it shows that beef contributes more to emission, more than milk, and that you can do that for other crops as well. So you plot the scatter plot, and it will show you the evaluation at the end. So the whole idea of this web app is to make a comparison between the two, so then our users can further choose which crop to prioritize based on their carbon emission. Yes, thank you very much.